All right, good morning, everybody. My name's Ivan Tolson. I work for a company named Green Button in Wellington. We do sort of supercomputing in the cloud, so being able to burst workloads to the cloud on demand rather than building your own server farm. We have a developer program, so if you're interested in that sort of thing, if you've got a high-performance workload, have a word with us, and we'll see what we can sort you out with. I named this talk after a Star Trek reference, and it's kind of apposite because I've got this alarming array of buttons and blinking lights and things in front of me. I don't actually want to go too close to them because I'm not sure what they do. And there's these big things saying don't touch. There's one that says matrix setup, and I'm worried that if I touch that, we'll get Keanu Reeves in here babbling weird conspiracy theories. So if that happens, I've touched the wrong thing. Unless you've been living under a rock or going to the SharePoint track for the last 3 days, you're probably aware that one of the big themes of TechEd this year is Windows 8, and in particular building Windows Store, what were formerly known as Metro-style applications. And if you've been to some of the talks on that, you'll be aware that we can write those applications in C++, C#, Visual Basic, JavaScript, but instead of targeting the .NET runtime, it's actually running on something called the Windows runtime, which handles it's got all these facilities for local storage and network access and streams and live tiles and XAML and all of those good things. And I want to talk to you today about the relationship between .NET, between your familiar C# and Visual Basic programming languages and the Windows runtime, how they mesh together, how they don't mesh together, what little subtleties you might want to be aware of. And we'll actually have a little bit of an explore inside the Windows runtime and see how it works with .NET. So at first glance, the Windows runtime offers a set of services very similar to what the .NET CLR, Common Language Runtime, offers. For example, it's got they both have well-defined type systems. Instead of just dealing with, say, pointers and flat sets of functions, they break things down into classes. Classes are described by metadata. Metadata is machine readable, so you can get IntelliSense on it, you can get compile time type checking, you can see the signatures of methods, and it can also group together methods so it can represent richer concepts of class members like properties or events. It can represent ideas like delegates. All these familiar things from .NET are available in the Windows runtime. There's also a strong component model, so in .NET you can build assemblies, and they encapsulate potentially complicated behavior behind a nice reusable simple API like a control or a draggable data component or an object relational map, for example, something like that. And Windows runtime has got the same kind of capability of packaging functionality up into components that surface only the API that you want. And in both cases, there's support for multiple languages, in particular for both C# and Visual Basic. So at first glance, you might think that the Windows runtime looks like .NET, but it's not. It's very different. And one place that we can see that is at there's a number of examples of that. One of those is native code support, for example. And this is one of the reasons why the Windows 8 team wanted to build a new runtime rather than relying on .NET. The Windows 8 core team regard C++ programmers or regard native code as a very important target. They're very concerned about performance. Whereas the .NET team are perhaps more concerned about productivity. They're willing to incur things like startup costs, garbage collection, running a jitter in order to make you guys more productive. The Windows runtime team wanted to offer native code programmers, people who wanted to write raw C++, that option. It also supports JavaScript, not the weird JScript.NET that some of you may remember from .NET 1. Does anyone remember JScript.NET? Man, that's gone down the memory hole, hasn't it? Man, dear me. Anyone remember J#? J#? Oh, a few more of you. Man, that's good. But the Windows runtime supports JavaScript running within Internet Explorer on HTML pages, not this weird dialect that you had to compile for the .NET runtime. The Chakra JavaScript engine inside IE10 will actually talk to Windows runtime classes. Windows Runtime enforces a stronger packaging and deployment model. In .NET, you would just have, you'd have a big pile of XCs and DLLs, and you copy them across somewhere, and everything would work. In Windows Runtime, because they want to support deployment through an application store, they've created a much richer concept of the manifest, a much richer concept of the container. So you will wrap things up into an AppX file. It will include a manifest that says what capabilities it needs, like does it need access to the camera, does it need access to the location, the device location. It also supports a lot of inter-application contracts that are built into the runtime, like search and share. In .NET, those had to be ad hoc. An application might support a particular WCF service, but there was no metadata to describe that. There was no runtime level concept of those inter-application contracts, only intra-application contracts. And there's a lot of changes to the actual APIs and to some of the details of the component model and the metadata. And I think that shows up that begins to show up some of the differences between .NET and the Windows runtime. So if we jump over into Visual Studio and I create a new project, so I'm going to be targeting the Windows Store applications all the way through this talk. But you can see there's two options there for creating a library in the Windows Store. There's the class library and a Windows Runtime component. Now, both of these we can write in C# or Visual Basic, and both of them are going to use the Windows Store profile of the .NET runtime. But we're going to see they've actually got some quite different constraints. So let's bring up the traditional class library, and I can make that public class hello, and I'll give it a and as you'd expect, that builds fine. And that's nothing complicated there. We've just got a little class in the public interface. What happens if I add another project, but this time I'm going to build a Windows Runtime component. And I'm still doing this in C#. I'm just going to take that code there, copy it across, simplest code you can possibly imagine, paste that in, build it, error. What's it complaining about? It's complaining that I'm not allowed to use, or it's complaining that Windows Runtime classes have to be sealed. That's a restriction that we don't have in .NET. Well, actually, it's a restriction that we don't have in the Windows Runtime either, but only internally. So we'll talk about that in just a moment. So if I make that modification, then I'm good to go. What happens if I want to make a generic class? Failed again. Not happy about having generic classes in a public interface because the Windows Runtime doesn't support that. Now, if I make this an internal class, then still getting used to this thing of having to seal them, but if I make it an internal class, you can see I'm allowed to unseal it, I'm allowed to make it generic. Once I'm inside the component, and I'm talking .NET to .NET, I'm talking .NET class to .NET class, I can do whatever I can use. I've got the full flexibility of the CLR available to me because I am running on the real CLR. But there are things I can't do at the public boundary. Another example of that is with structures. So let's create a simple struct. And that's an impressive number of errors for such a small type. What's it complaining about? Well, it's complaining about a number of things. Firstly, it's saying that, well, fundamentally what it's complaining about is the Windows runtime structures can only contain public fields. So what I've got there is I've got a couple of properties, and it doesn't like having properties in a struct. Those properties are implemented in terms of get and set methods, and it doesn't like having methods in a struct. And those properties, because they're implemented by the C# compiler, are backed by private fields. And it doesn't like having private fields in a struct. The only way to make the compiler happy with Windows runtime structs is to have them containing only public fields and nothing else. By contrast, a class is not allowed to contain a public field. It can contain private fields, that's okay, but not public fields. So you've got all these odd little restrictions. Other ones are, for example, you can only derive from Windows runtime types, or you can only implement Windows runtime interfaces. One rather frustrating little quirk of that will be that you can't create your own exception classes anymore. You can only use the ones that are supplied by the Windows runtime. Again, remember this constraint only applies to public members of your component, to the public interface of your component. If you want to create internal exceptions for your component to throw to itself, then that's fine. You can do that as much as you like. But at the boundary, there are a number of constraints. Yes? I believe it gets translated into a COM exception. Yeah. Sorry, the question was, what happens if an internal exception leaks out? So what happens if I declare an exception as internal, I throw it within one of my methods, and I don't catch it, so it escalates up across the Windows RT boundary to some other component. I mean, you've kind of got the same issue in .NET. If you throw an internal type, then that could potentially leak across component boundary. So it can happen anyway, but I believe that will get translated into a COM exception. A couple of other limitations that you'll run into. You're not allowed to have ref parameters in a Windows RT method signature. So it's not going to be happy with this one. So if you want to do something like that, then you will need to use an out parameter instead, which it will be happy with if I supply a... Oops. One particularly weird constraint that you may run into is if you're passing arrays back and forth and planning to mutate them. So in the Windows runtime, arrays are either passed into a function or they're passed out of the function. The function can either read from them or write from them. It is not allowed to mutate them, or if it does, the mutations, the changes will not get passed, will not be returned to the caller. They're being made on a private copy. So arrays are not being passed by reference the way they are in the .NET framework. So that's another little thing to watch out for. And again, the compiler will give you a little bit of help with that, though not everything. So I think the best way to sum it up is with a piece of wise advice. You will not necessarily be able to recompile your existing components as WinRT components. Now, that's not necessarily the end of the world, because you can still recompile them, or you can still build them as CLR components targeting the Windows Store profile. So if we go back and look at that little solution there, if I create a class library project, that's going to build a .NET DLL, and that can be consumed by other .NET components, and it can use the full capability of the CLR in its interface. But it can only be consumed by other .NET components. It cannot be consumed by C++ or JavaScript, because it's purely a .NET class library. It only has .NET interfaces. When I build a Windows runtime component, the compiler is doing some additional work to make it available to the Windows runtime. And because the Windows runtime has got a slightly different type system, it limits the public interface to what is available in both type systems, to what is available in the intersection of those two type systems. One thing that you will no doubt notice as you work with the Windows runtime is that WinRT itself does contain generic and unsealed types. So, for example, I can have something here that consumes, say, an I list of strings. Now you might think, well, that's a generic type and it's in the public interface of a WinRT component, but actually that's fine. Similarly, if you look at the XAML hierarchy, if you look at the control hierarchy in Windows Runtime, that contains unsealed classes. You've got, control, inherits to content control, button-based button. You've got these really long XAML-style inheritance hierarchies. What's going on here? Well, it turns out that the Windows Runtime is giving itself some special consideration, which is very unsporting of it, but that's just the way it works. Why do these limitations exist? Well, the reason for not allowing, say, unsealed types is because JavaScript doesn't support inheritance. JavaScript is a prototype-based object system, not an inheritance-based object system. So if we were allowed to build inheritance hierarchies, it wouldn't be possible to project those into JavaScript in a terribly sensible way. And JavaScript is meant to be a first-class citizen of the Windows runtime. So we're not allowed to create those things. Now, the Windows runtime is allowed to do that internally because the JavaScript projection, the language projection, which we'll talk about later on, has special handling for that particular case. It understands that case, and it can cope with that. The argument with generic types is very similar. Under the covers, generic interfaces like iList of T and iDictionary of T to of key to value, these are defined by WinRT. They're represented in WinRT by what they call parameterized interfaces. But it's up to language projections to decide how to represent those parameterized interfaces in any given language. In the case of .NET, they represent them as generic types. In the case of C++, they represent them as C++ template classes. In the case of JavaScript, they don't represent them at all because JavaScript hasn't really got a concept of types like that, or it doesn't have a strong concept of types in the same way, so it's not a problem. But notice that's having to be worked out on a case-by-case basis. So if we were allowed to create our own arbitrary generic types, then the projections would not know what to do with them. And therefore, rather than risking things being confused, rather than risking the fact that it's risking not being able to use a component from C++ or JavaScript, they've just said you can't have those in the interface. If you want to have those, you have to make them internal and expose some more strongly typed, more well-defined, non-parameterized interface. One quick caveat, by the way, one option that you'll see in Visual Studio new project dialog is what they call a portable class library. Portable class library is still a .NET class library. What the portability means is it's portable between the different .NET profiles, but it's still a .NET class library, not a Windows runtime component. It is not usable from C++, it is not usable from JavaScript, but it does mean you can use anything you want to in the public interface, subject, of course, to the profile restrictions on what APIs, what types, what assemblies are available. All right, we've talked about the language projections, and I want to just go into a little bit more detail about those. So the Windows runtime can actually appear differently in different languages. In .NET, if you define a type in your component, you're pretty much expected to appear the same no matter what language is consuming it, whether it's being consumed from C# or Visual Basic or F# or Iron Ruby or Iron Python or IronJS or Jurassic or whatever. You'd expect it to look pretty much the same way. Windows Runtime deliberately moves away from that assumption. It says you've got a language that you love, whether that is C# or Visual Basic. Does anyone love Visual Basic? Yay! Fantastic. That man gets a Mindscape Megapack. See me afterwards, you get a Mindscape Megapack. For confessing to loving Visual Basic. All right, so they want you to, so in C#, we've got a standard library. C# Visual Basic, we've got a certain standard library, the .NET framework, the BCL that we expect to be able to use. C++ programmers have got a standard library, the STL that they expect to be able to use. They expect to be able to use STL algorithms, iterators, and things like that. JavaScript guys have got standard features like JavaScript arrays. They've got things like the push method on arrays. And the Windows runtime goes out of its way to say you should be able to use the idioms, the names, the types that you are used to in your favorite language, rather than having to adapt to what the framework is giving you. So let's take a look at that. So here I've got a very simple Windows runtime component, and I've put a method on it which returns an ilist of string. So far, so good. I'd now like to consume that in C++. So here is a little C++ application, and I'm going to use my component, and I'm going to call it getSomeStrings method. And look at the return type of getSomeStrings. That is not a .NET ilist of system.string. That is a C++ iVector of platform : string. Don't worry too much about the little hat things. Those are a piece of syntax it's kind of borrowed from C++ CLI to try to make C++ programmers' lives easier. But under the surface, this is all actually compiling to native code. This is not compiling something like IL. This is not C++ CLI, even though it kind of looks at it. And you can do the Windows runtime in raw C if you're really, really masochistic. There was a great post by Ian Griffiths, which he published shortly after Build, great blog post, well worth looking up, where he actually tries to program the Windows runtime in raw C, right down at the pointer level. And it goes on for several pages and still doesn't work. But it's very educational. It's worth checking out. Okay, so something is fishy here. We declared a getSomeStrings method that returned a .NET ilist of T. But when we used that in C++, we found that it appeared as something completely different, some weird C++ kind of type. Similarly, if I write a component in C++, say this, here's a component that returns an IMAP, or an IMAP view, which is a read-only view over a map. What happens if I try and consume that component from .NET code? Well, there we go. I can instantiate that component, and I can call getMap on it. What's the type of that? What's the type that comes back from that? I don't know if you can see that too clearly, but that is an iDictionary. Familiar .NET system.collections.generic iDictionary of string to string. So somehow an IMAP is being translated in the other direction into an iDictionary. If that's not weird enough, it gets weirder. So let's take a look. Let's not do that. Let's take a look at our C++ usage of that map. And excuse me. Let's look at some of the methods on the map type. So it's got an insert method. It's got a lookup method. You can pretty much guess what they do. There's going to be no surprises there. What happens, but what have we got in dictionary? Well, we've got the familiar .add, and we've got this indexer. We don't have a .insert method. We don't have a .lookup method. So somehow, not only have the types been renamed, but the methods have been kind of renamed or remapped or something like that. Now, you might be thinking, oh, I know what's going on. It's kind of making a copy or something like that. It's copying the data across, and then it's something like that. Well, no, because what we can see is we can do a getMap. We can then modify that dictionary in .NET and then get the view back again. So we can round trip that dictionary between C++. We can create it in C++, hand it a reference to .NET, modify it in .NET, and C++ will see the changes. So if I run up my terrifically exciting Hello World application, the suspense, and have a look at the debug output, you can see that we have successfully added things. We have successfully added something to that dictionary, and it is the same actual object. It's not like there's some weird copying thing going on. It's not like we're getting a clone of it. We are actually both working on the same dictionary or the same map, whatever it is. We don't really know. So this raises the question of what is the actual truth? Is it a list? Is it a vector? Is it a dictionary or a map? Is the method called add or insert? And the Windows runtime, I know this is a very philosophical kind of a slide. I'm hoping someone can help me with the answer. The Windows runtime is almost an unknowable truth. It is this thing that is out there. There is a real Windows runtime, but you can approach it only through the language projections. You do not work with it directly, unless you're Ian Griffiths and you're crazy. You do not work with it directly. You approach it through the language projections. You use it through JavaScript, through C#, through Visual Basic, through C++. And in each case, the language, the compiler, the Windows runtime wrappers give you a little bit of a layer that insulates you from the raw horror of what's going on under the surface. They will adapt it to be what is most suitable to you, the thing that you know that you are already familiar with. The language projections go even further, though, than just renaming stuff or just backing familiar types onto unfamiliar types. Let me give you an example of events in the Windows runtime. So in .NET, you're familiar with the way that events work. You declare an event, and you can plus equals a delegate, and then you can minus equals the delegate to remove it. In WinRT, they've taken a slightly different approach, which is that when you subscribe to a delegate, when you add a delegate to an event, it gives you back a registration token, a cookie effectively. And when you want to remove that subscription, you hand back the cookie rather than handing back the delegate itself. But if I look at my Windows runtime component written in C#, I still just declare an event. And when I use it in my Windows runtime application, I just do a plus equals and a minus equals using the delegate. So what's going on there? Well, if I build that and I take a look at what's been built, look at that subscription. You might not want to look too closely because it's a bit on the gnarly side, but what's going on there is it's calling Windows Runtime Marshall.addEventHandler, and it's passing all sorts of crazy stuff. In the removal, it's calling this Windows Runtime Marshall.removeEventHandler. So it's not doing the usual thing of just calling the add and remove methods that the compiler has generated for you. It's doing something. It's invoking the Windows runtime to adapt the .NET event pattern to the Windows runtime event pattern. So this thing that's happening inside the C# compiler. This is no longer the CLR doing the magic. This is the C# compiler itself doing the magic. So for your compiler to target the Windows runtime, the compiler actually needs to be updated to be aware of the language projections. Language projections are happening. The CLR and the C# and VB compilers are conspiring to make the language projection work. It's not happening on its own, and neither one alone is capable of doing it. So the idea of language projection is that they give you a seamless experience as you move from a .NET, or a .NET or C++, a traditional, if you like, background into the world of the Windows runtime. You can carry on using the stuff that you want to use in the way you expect to use it. But language projections do leak somewhat. They don't leak an awful lot, but you can kind of see the chinks of truth through the leaks and the abstraction. For example, in .NET, stream is a class. In the Windows runtime, there is no stream class. There are a bunch of interfaces like iStream, iInput stream, iOutput stream, iRandom access stream, all these various interfaces. And the language projections can't really adapt between classes and interfaces because of things like the base class problem. You can't have, if you had an iInput stream that happened to derive from something strange, then you might run, and you adapted that into a stream, then you kind of you'd have some problems with the fact that actually now it's part of two classes, and we don't like the look of that. So in that case, the .NET people have resorted to a bit of manual fixing up. So say a Windows runtime method that, say, returns an iInput stream will still appear in .NET as returning an iInput stream, not a stream class. And it's up to you to call an extension method to make the adaptation to a .NET stream. So, for example, here in my C++ component, I've got some members here which return stream interfaces, and I've got one which takes a stream interface. If I look at how I call those in .NET, if I try to simply rely on the language projection to do that mapping for me, it complains. It says that's not a valid assignment. So I have to bring in this asStream4Read extension method. And so that's an extension method on the iInput stream. Similarly, the other way around, if I've got a .NET Stream object, I can convert that into a Windows runtime interface of the appropriate time. Obviously, in this case, it's my responsibility to make sure I know how the stream is being used. Another example is, of all things, strings. Now, you kind of think that strings would be a pretty non-leaky abstraction, but the Windows runtime, bless its cotton socks, has introduced yet another new string type, because I don't think we had enough of those already, called the H string. And H strings are non-nullable, which is a jolly good thing. But it causes a problem for .NET where the string type is nullable. In the Windows runtime, null is identified with empty. In .NET, those are separate concepts. So what happens if I try to pass a null string to the Windows runtime? Well, here's a process string method implemented in C++. And the H string is projected into C++ as a string hat, platform string. You can see that method does absolutely nothing. It doesn't make any kind of checks, doesn't make any kind of reliance on the string, so I've not written any code in that method. So what happens if I call that method with a null string? Well, firstly, obviously, I need to get rid of the nonsense code that I commented out earlier by, there we go. And now if I step over that, bam, I get an argument null exception. Now, my code did not throw that exception. You saw my C++ method. It didn't make any checks on the string to see if it was null. So the CLR is actually saying, before it calls into the Windows runtime, it's inserting a null check for strings because it knows that it can't represent null strings faithfully in the Windows runtime. Conversely, if I have a method that returns a null or null PTR from C++, I can still call methods on that because it actually comes back as the empty string. The two are identified in the Windows runtime, which they aren't in the CLR. The Windows, I've said that you would normally approach the Windows runtime through the projections. There is a source of truth. In fact, there are several sources of truth. We talked about the Windows runtime providing metadata, machine-readable metadata, in the same way that, say, a .NET assembly provides metadata about the types and the methods and so on. In the Windows runtime, these are stored in WinMD files rather than in the DLLs themselves. But fortunately, the guys who designed the Windows runtime decided to pretty much reuse the .NET metadata format for their WinMD files. And if you look in Windows System 32 Win metadata, you can see the WinMD files for the Windows runtime itself. And these are not just like reference assemblies for your compiler. These are things that actually get used at runtime. So in particular, the JavaScript engine needs to be able to resolve names to actual properties and methods at runtime, and the WinMD files are part of that. But because they're so similar to the .NET DLL format, I can actually bring them up in ILDASM, which very annoyingly will not remember my font settings. So I can actually go and have a look in here. I can have a look in the winners.foundation.collections namespace, and look, there's the truth. There's the IMAP type, there's the iVector type. So we can actually see what the real types are that underlie the language projections. And in most cases, what you'll find is that the C++ language projection is generally pretty true to what's going on. Not always. There's some stuff it does with the platform types, like platform string and platform object. But generally, the C++ projection is pretty close. The .NET one, you can see, for example, here's the equivalents to IEnumerable, IEnumerator, IDictionary, IObservable collection, IRead-only collection, iList, things like that. And you can see there's been some substantial tweaks done to in the .NET language projection. So what does this mean for our own components? Well, we can use ILDASM to look at the what's been generated, what metadata has been generated, what signature has been generated for our own components. So here's that one that we built earlier. And there's our hello component. Just up the font size again. And let's take a look at this my component thing. Let's take a look at, say, getSomeType. So getSomeType was declared in .NET as returning a type. You can see what's actually been emitted by the compiler is something that returns a windows.ui.xaml.interop.type name. That getSomeStrings is returning the Windows runtime iVector type. You'll also notice while we're in here that there's a bunch of stuff that we didn't define. So the stuff I wrote was my component. But what's this? What's this IMyComponent class? Someone's defined an interface for us, which I didn't ask for. Well, it looks like it's pretty similar. It's got the same kind of signatures in it. And in fact, if we look at my component, you can see it implements IMyComponent class. There's some other stuff in here as well that I'm pretty sure I didn't write. I'm pretty certain I didn't write that because that's a weird name. I mean, I like giving things weird names, but even I have my limits. What happens if I look in here? Well, this looks, again, the same kind of things, except that now, whoa, that's returning a type. That's returning an iList. This looks much more like .NET stuff. And in fact, if we compare the headers here, you can see that my component, if you look there, the class is decorated with the Windows runtime keyword. And if we look at the methods in it, you'll see that they are declared as runtime managed. Whereas if I go look up here, the class does not have the Windows runtime keyword, and the methods in it are declared as CIL managed. Also, down here in the real library, no implementation. There's no code in there. The code is all in this funny brackets CLR library. And there's the IL bytecode. We can see the same thing if we look at the C++ component, or we can see a similar thing if we look at a C++ component. So now here, we're not going to see any code because it's all native code. There's no IL for it to disassemble. But the metadata is still emitted in a format that ILDASM can understand. And there is the component. That kind of looks like the stuff we saw earlier. But again, notice that it's emitted this interface, this __I myCPP component public non-virtuals. Snappy name, guys, which contains all of those methods. Another intriguing little quirk of which I should have shown you from here is, I hope you can see this, I don't need to update it, but there's also a separate interface for the static bit. So I defined a static method on my component class. And if we look at the interface, that doesn't appear. So the static method was this get number of days in week. That doesn't appear in the myComponent class, but it appears in this additional interface, myComponent static, which I didn't write. Now, interfaces can only have instance members, so somehow, somewhere under the covers, the compiler has taken this idea of a static member and translated it to an additional interface, which is going to appear as a singleton or something like that, and is going to contain the static members. So there's a lot of magic happening under the surface here. Something else I want to show you is how the Windows runtime actually loads these .NET assemblies, these components that are compiled in .NET. And you might think, well, this is the usual thing. It's going to use the same kind of approach as .NET, where you just put the assemblies in your local directory, in the private directory, and they just get picked up as if by magic. In fact, that is not what happens. During the install process from the Windows Store, which is something that Visual Studio basically emulates when it does a debug, they actually have to be put in a catalog. And we can have a look in that catalog. And can you guess where the catalog is stored? Here we go. So if we have a look, so this is one of our applications, and you can see it's got these activatable classes underneath. It's got an application class, it's got a C++ component, it's got the hello component, it's got some other classes that we emitted. So it's basically a catalogue of all the classes that application is using, apart from obviously the ones in the core Windows runtime. And you'll notice some stuff that may be familiar if you're kind of old school. You notice they've got these class IDs, and they've got a DLL path telling you where the DLL is that contains that component. So in the case of the C++ component, you can see that the DLL path is the C++ component DLL itself. I hope you can see that reasonably well up the back. I'm not sure if I can increase the font size on this. In the case of the hello component, the one we wrote in .NET, DLL path for that is C Windows System32 CLR host.dll, not the DLL file that we built. Because if we go back and look, we don't have a DLL file. We only have the WinMD file because our IL code got stuffed into the WinMD rather than being emitted as a separate DLL. So what is this CLR host.dll thing? Well, we could try running ILDASM on it, but because it's called CLR host, I'm kind of guessing that it's probably not a .NET DLL. I'm kind of guessing it's a native DLL. Fortunately, we have got a tool that we can use to find out what is exposed by a native DLL. It's called dumpbin, and I can never remember the exact syntax for it. There we go. So it exports only one thing, which is this DLL get activation factory. So that's a global method exported from the DLL. If I have a look at my C++ component. You can see that exports two global methods. It's got that same DLL get activation factory. It's also got a DLL can unload now. So it looks like what's happening is the Windows runtime is going to go to these DLLs and ask to activate classes somehow. How can we find out what it's doing? Well, what we can do is we can set a breakpoint on CLR host DLL, DLL get activation factory, and see what gets passed into it. So let's jump in here. And I think we need to change that to C++. And we need to run that from here. And if we run that up, then if we look at the call stack, again, hope you can see this at the back. If not, you have to take it on a bit of trust. We've broken at CLR host DLL somewhere inside that. I'm not going to show you the disassembly because I don't understand x86 or x64 assembly language, and I'm guessing a lot of you would not find it terribly useful either. What we can do is we can have a look up the call stack, and in particular when we get, say, around here, this is in a little helper header file for C++, and you can see that what's being passed down is, oh dear, let's just get in there, there we go. What's being passed down is that string, hello component.myComponent, the type name of the type that the Windows runtime wants to activate. So CLR host is being given a name of a class to activate, and it's going to it's going to spin up the CLR in process. It's going to locate the relevant type, the relevant .NET type, which is actually going to be that CLR type, and it's going to call the constructor on that. Now, if you've been around for a little while, you may be getting a really nasty feeling right now, little kind of collywobbles in the tummy. We've seen the registry. We've seen functions called DLL can unload now. We've seen something that looks awfully like DLL get class object. We've seen a hosting DLL for proxying .NET types to be activated. We've seen everything being moved out of classes and into interfaces. Even static things are being moved into interfaces. We've seen structures that are C-style. They're only allowed to contain public fields, no methods or anything like that. And this may be bringing back some memories of late 90s, early 2000s. It's Keanu Reeves with the crazy conspiracy theory. I warned you this was coming. I pressed the wrong button. What if the Windows runtime is really COM? Well, yeah, it is. That's what's going on under the surface. Now, it's unfair to just say, oh, we're going back to COM. The Windows runtime is COM. The Windows runtime is a lot more than COM. It's a whole bunch of services, a bunch of new interfaces, a bunch of new runtime features. It's a bunch of new packaging features. But it does build on the COM infrastructure. The underlying infrastructure is not .NET-ish, it is COM-ish. That is why you have interfaces. Everything goes through those interfaces, not through the something like CLR method call. But you don't need to worry about that, he said confidently. Although at the infrastructure level, at the operating level, at the runtime level, everything is interfaces, everything is COM, you don't interact with that directly. You interact with that indirectly through the language projections. And the language projections give you this class-based view, this .NET style view, this JavaScript style view of this stuff, which saves you having to interact with this stuff. But, as we've seen, the abstractions are occasionally a bit leaky. Bevan asked a question earlier on about exceptions, and you can now see why things happen the way they do. You can't define your own exceptions because COM doesn't have exceptions. COM has H results. And all that the Windows runtime is doing is projecting certain H results, certain known H results, into certain exception types in much the same way that the CLR did. You can't define your own exception types because you can't influence that mapping. You have to use COM exception with your own H result. That's all that the Windows runtime knows how to project, or all the language projections know how to project. So what does this mean for runtime implications? Well, let's talk about the various different directions. So when you call from .NET code into a native Windows runtime component, like a C++ component, you're actually using .NET COM interop. What will happen is that the CLR will spot that you're trying to activate a Windows runtime type. It will locate the DLL using the registry, and it will call that DLL, it will call the Windows runtime to locate that DLL, and the Windows runtime in turn will call that global DLL get activation factory. Now this may be in your native component, or in the case if you're CLR component, it will be in the CLR host.dll, but eventually it comes down to DLL get activation factory with the name of the type that the CLR is asking for. That's going to return an iActivation factory interface, which, for those of you who remember, your COM is kind of similar to an iClass factory interface. It's a bit more flexible because as you traverse easily to different constructors. So, for example, in COM, you could only have the default constructor. You could only do a co-create instance. You couldn't pass parameters to it. In the Windows runtime, you can have custom constructors, and the runtime, the iActivation factory plumbing, will find its way around those constructors, match things up, and call the right one for you. So the CLR eventually calls the iActivation factory.activate instance, or the moral equivalent, depending on what the constructor signature is. That will return a native object in this case, because we're assuming we're calling from .NET code to native code. And .NET, the CLR, will then wrap that native COM component in a runtime callable wrapper, an RCW, just as when you did import a type library into your .NET project and called COM objects through that type, through the imported type library, again, the .NET runtime is constructing an RCW, a runtime callable wrapper. So the plumbing is the same, pretty much. I'm sorry, can you say again? Can you still use variants is the question. No, you can use object instead. I don't believe that variants are supported. There's quite a lot of limitations, like I said, on what can go into a Windows runtime interface. In particular, there's some limitations around things like, I don't believe variants are supported. But because you can use object, because you've got strong type information anyway, you've got reflection capability within Windows runtime, you don't really need variants as much as you used to back in the good old days. You can pass object and then you can just do a get type on it to figure out what type it is and process it accordingly. Also, variants are scary because they keep changing out from underneath us, which frightens the Windows runtime people. What about when you call from native Windows runtime code, like C++ code, into .NET? So you try to activate a .NET component. Well, we've kind of seen what happens there. CLR host.dll exports a DLL get activation factory method, and again through the same plumbing, the RO API, the Windows runtime calls that DLL get activation factory, gets an iActivation factory back, instantiates the component. CLR host will spin up the .NET runtime, spin up the CLR in process if necessary, if it's not already been activated. And obviously, what will come back from the CLR, from iActivation, from the activation factory, from the constructor, is a .NET object. because the Windows runtime code is native code, it's COM code, it needs a COM callable wrapper around that. But again, this is existing infrastructure in .NET. We've always been able to register .NET components as COM components. Previously, we were calling them through iDispatch or through strong-typed interfaces. Now we can call them through the Windows runtime, but the mechanism is still the same. You get the runtime, the CLR constructs a COM callable wrapper around your object, and what the runtime, what the native code sees is that COM callable wrapper. It sees those COM interfaces. And those COM interfaces are, of course, things like the IMyComponent class that we saw earlier in the ILDASM. When you call from .NET to .NET, you don't go through any of this malarkey, any of this craziness. So if you've got a .NET assembly and you're calling that from another .NET assembly, then it's just going to use .NET loading. It's only when the Windows runtime is in play that it goes through all this row get activation factory, DLL get activation factory, iActivation factory, get instance, yada, 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 wrapper. When you're just calling .NET to .NET, it's just like you've always done. So when you write, if you're building an application in C# or Visual Basic and you want to write components in C# or Visual Basic that are going to fit into that application, you can still do so. Nothing changes. It's only if you want. It's only when you're going through the Windows runtime, through those interfaces, through those component boundaries, that the Windows runtime actually comes into play. And finally, of course, native to native. That's just ye olde traditional COM call. When you're calling from JavaScript into the Windows runtime, again, that's kind of handled by the Chakra engine within Internet Explorer. Again, that's using the WinMD files and COM under the surface. If you've done stuff with, I think this goes all the way back to IE4, ActiveX controls. Weren't they a great idea? We've always been able to call COM components from the Internet Explorer JavaScript engine. This is kind of just building on that functionality and, of course, greatly enriching it with the additional metadata. One thing I probably ought to reassure you about is when we looked in the registry, these registrations here, you can see they're under individual packages. So I think there's another one where you can see the hello component is actually separately registered. The separate catalogs for each application effectively. So when an application is deployed, it is very much the same as .NET. Everything goes into the application container. It goes into a private area, and applications are isolated from each other. They do not interfere with each other. The registrations are not global. This time for sure, there will be no DLL hell. Whoa, they're not buying it, guys. I wonder why. Yeah, we have heard it before, I know. There is, in fact, unlike .NET, there is actually no GAC in the Windows runtime. There's no global assembly cache. Everything is, yes! No global assembly cache. Thank you. Everything is private, except, of course, the core shared Windows runtime itself. It's kind of strange looking back at this point and seeing that in the late 90s we had COM, we had this very lightweight, well, kind of lightweight, it started out pretty lightweight, this efficient native code-oriented runtime. And because of a lot of weaknesses around, say, the reference counting model, the very weak metadata model, IDL versus TLB craziness, the non-extensible metadata in COM, we moved on to .NET. We deliberately went to a multi-language runtime that was built for multiple languages from the ground up, where IL would be the lingua franca. Every language would actually resolve to IL, and that would underlie everything. And now the pendulum swings back. In the 2010s, we're seeing the coming of the Windows runtime based on COM, and strange enough, IL is just another language that sits on top of this layer. It's not quite as simple as that, because as we've seen, the compilers that go from C# or VB to IL still having to do some magic. But IL is on a par with C++ or JavaScript. It's no longer a target. It's now actually a consumer of the multi-language runtime. Just another language in the bag. So, what do I hope you've got from this? Well, the important thing to understand is that when you're writing C# or Visual Basic, you're still writing .NET. You still have the full capability of the CLR, the full capability of the type system, the full capability of the metadata at your fingertips. You have some limitations on the APIs because the Windows runtime sandboxes you more firmly than the .NET runtime. And of course, it's very limited. It's limited to building Metro-style applications. You don't have things like ASP.NET in the Windows runtime profile, in the Metro profile, in the Windows Store profile. But it's still .NET. You can still use all of the good things. You can use events, you can use properties, you can use generics, you can use inheritance, you can use all of those things that we're used to in C# or Visual Basic. And it's running on the real CLR. It is real IL. We've seen it being disassembled there. We've seen IL code. You can take it apart in Reflector or .peak or whatever. It's real IL. It's running on the real CLR. But at the boundary, there are differences. The Windows runtime type system is not 100% compatible with the .NET type system. And when you're trying to talk to other languages outside IL, outside the CLR, you need to be aware of what those differences are. So the details may have changed, but your investment in .NET remains safe. You can still build class libraries. You can still build applications. Nothing of that's changed. What you can now do is you can now reach out to C++ and JavaScript developers and extend your reach to them. You can interoperate much more seamlessly between native code, games or whatever, between HTML pages with JavaScript on them and your .NET code in a much more transparent way. Just a couple of final public service announcements. Firstly, if you need to get hold of me, if you've got any questions or you want to give me any feedback or you want to get hold of anything, then you can get hold of me on those contact details. The guys at Mindscape, my former employer, they're offering a free mega pack in addition to the one that we're going to give away to Visual Basic Man up there. So if you leave a business card with me or just leave it up the front, I'll pass it on to the Mindscape guys and you'll go into the draw for a free mega pack. I've also been asked to say that Green Button, my firm, is hiring. We're looking for developers. So if you're interested in building the next generation of cloud applications, supercomputing applications, get in touch with me or visit the website. But, oh no, I'm not going to show you boring TechEd slides. Come on, man. Let's go back. Wrong direction. So to reiterate, it is .NET. It is not as we know it, but it's still .NET. You can still do everything you're used to. You've still got the full power there. You can now go, though, so much further. Go away and build great applications. Thank you very much.